Okay, functions as power series. So let's say we know the following. All right, we know that 1 over 1 minus x can be expanded if x is between minus 1 and 1. Okay, I want you to note that it doesn't work at either endpoint. At the endpoint where x is 1, it's obviously just 1 plus 1 plus 1, so that's not going anywhere useful. And the endpoint where x is negative 1, it goes 1 minus 1, plus 1 minus 1, plus 1 minus 1. Okay, so that doesn't do us any good. But we're going to do a cute algebra stunt. We can replace the x with something else. So for example, what if we wanted to know just any old thing? Can we do this? Is this legal? Guess what? Yeah, it's legal. It's totally awesome. All right, so we're actually replacing x with minus 3x squared. How about that? And we also have to bring this guy along. So the minus 3x squared has to be between minus 1 and 1. So obviously that negative sign is just going to go away. All right, x squared has to be less than a third. So x is, plus and minus square root of a third. That works. Okay, does that work? I think that works. Okay, that's pretty amazing. So we can do all sorts of stuff. So we can do like 1 over 1 plus x squared is equal to 1 minus x squared plus x to the 4th minus x to the 6th, so on and so forth. And we can adjust these constants pretty nicely. So here's some examples. We can do 1 over x plus 2 is equal to what? Well, it doesn't seem that profound, but we go 2 plus x, right? And then factor out a 2. Now what do? Let's see, go 1 plus x over 2. That's it. So we have preserved this structure. So let's say this is actually 1 minus negative x over 2. All right? So we're going to just say, all right, we had 1 plus minus x over 2 plus that same piece squared plus that same piece cubed. Okay? So it's, oh, and we have to pull the r. So we have to know that that piece is less than 1. So that x over 2 is between 1 and negative 1. So x is between negative 2 and 2. Okay? Great. So now what do? Well, we could just be nice and write this properly. So let's go ahead and do that. Now, this 1/2 right here just comes along for the ride. And then this piece right here, which was playing the role of x, but it's minus x over 2, it just gets placed right here to the power of n. There we go. Okay, voila. Not too bad, right? Not too hard. Now, we can check this if we want, but I don't really want to. I'm just going to just quickly tell you what you would do. Okay. And if you multiply by x over 2, you're going to get like multiply by x over 2, you're going to get that piece again, but it's going to alternate. So all these guys are going to cancel out, and then you're going to get s plus x over 2s is 1/2. Okay, and then you just factor everything and solve for s, and when you're done you get s is equal to 1 over 2 plus x, and so you're happy because you got back to what you started. Okay? Alright, so next thing, in class I called this theorem of awesomeness, and the reason why it's so awesome is it just allows you to do this really cool, awesome thing that you wouldn't think is possible. All right, so we have a power series about A with a radius of convergence that's non-zero. So this doesn't make any sense if radius of convergence is 0, because then the whole thing only converges at a point, and then the following thing we're about to do would make absolutely no sense. But assuming there is some reasonable radius of convergence, you are allowed, in other words, this works, to find the derivative and the integral term by term. Okay. And bonus, you get R for free. I mean, like, you don't have to calculate it. It just comes along for the ride. It is so cool. Okay. So why is this really amazing? Okay, here's why it's amazing. Because you have some function f, and there's nothing saying that the convergence cannot look like this. I mean, this, what if you have this wiggle waggle thing going on, and as long as you stay within a strip of f, you're considered to be converging to f, right? But that's not what we're saying. We're saying this is even a stronger kind of convergence than that. Not only are we getting closer and closer to f, but all the derivatives are getting closer and closer to f. So it's not okay to wiggle, wiggle, wiggle. That's forbidden. It has to hug the curve and the derivatives. Is that crazy? Okay. So it means the derivatives come along. That's just totally amazing. This is just totally amazing. And what I'm actually making reference to is we are very, very soon going to talk about Taylor and Maclaurin series. And so this is all kind of a foreshadowing of that. This is all coming together. These are a whole bunch of little theorems that are coming together. It's very, very cool stuff. Okay. So, for example, what's the derivative of this guy? Remember, this is the guy we know how to approximate, right? So maybe we can harness that. Okay, here's the derivative. If you don't believe me, calculate it yourself. So here's the cool thing. Let's just put our series right in here, because we already know that it equals that. So we're saying, I'm purposely writing this wrong. I'm going to fix it. Okay, so I'm saying that term by term, okay, I can take the derivative, right? So you see how I'm taking the derivative piece by piece? Now what is wrong with this? I purposely left something wrong so we could talk about it. Okay, this n equals 0. That's wrong. Why is that wrong? If you put 0 in here, here's what's going on. So I'm going to cross that off just so you know that that's wrong. If I have y is equal to 3 plus 4x plus 7x squared, and then I took the derivative, the 3 would disappear. It wouldn't turn into 3 over x. It would just disappear. And the 4 and the 14x, they would do what you expect. So those terms are okay. But we want to make sure that whatever constant term we have over on this side for when n equals 0, that piece has to disappear. And unfortunately, it didn't disappear. We can make it disappear by simply starting the summation at n equals 1. Now, we got away with it this one time because n equals 0 will cause that n to be 0, but we don't want to rely on that because that stunt doesn't necessarily always work. So just when you're integrating, you always have to worry about the constant of integration and make sure you calculate it correctly, but when you're taking the derivative, you have to worry about changing your indices. So whether you differentiate or integrate, you just have to be careful with what you're doing with your indices. So always watch out for the pitfalls. But other than the pitfalls, if you just tiptoe around the pitfalls, there is no problem. So let's go ahead and then I can shift this index actually. And this is something that I encourage you to learn how to do. All right, and it's a difficulty for math students, and it's a difficulty for computing students. It's something that definitely takes practice, but you have to learn how to shift indices. So it does not necessarily come naturally. So what happens is when the index goes down, for example, n starts at 0 instead of 1, every instance of n has to go up. So they're counterbalanced. So the index goes down and the instances go up. Okay, they're contrary motion, if you want to think of it that way. Okay. What is left in this? All right, I'll just keep going ahead. You guys can pause the video. So, question. Find power series representation for natural log of 1 plus x and the interval of convergence. Okay, so let's do that. Well, f is natural log of 1 plus x, derivative 1 over 1 plus x, and just if you rewrite it, 1 minus negative x. Fine. So the derivative is this guy over here. Now we know how to write that. There we go. So let's integrate the derivative to get back to the function. Okay, so term by term, and then of course we're going to worry about the constant of integration. So, and we did this in class, nobody had problems, so I'm just going to write it down. But plus c. So this is the part you have to watch out for. What is the plus c? Well, you go back to your original function. Natural log of 1 is 0. So in this case, c equals 0. This time, we are lucky, so we can get rid of it. Okay? And again, the book pulls out the negative, and it changes the index, so it makes you start at 1 instead of 0, and then it makes the exponent n, and then you divide by n. It's all equivalent. I don't care. Okay, so I'm not going to squabble about where you start your sum, as long as what you have is correct. And I don't care how you package the -1, as long as it's in there somewhere. Please try not to mimic the horrible format of the web work questions. And I don't mean that the questions are horrible, but the format, they make you do things like, 3 squared in the numerator to the power of n and the denominator 10 times whatever. Those are student exercises, so don't copy that format. Okay, you're supposed to make it look clean, but as long as it's clean, I don't care what format. Okay, so, oh yeah, so the question also said interval of convergence. Okay, so we know that in the original situation over here, we had this kind of thing going on. So we actually know that x is going to go -1 to 1, but then we don't know about convergence on either end. So let's go ahead and look and see. So for one, we can take a clue from the actual function. If we put a -1 in for x, we get natural log of 0, and that's -infinity. So the function itself isn't good there, so we know that there's not going to be convergence for the series. I mean, think about it. Or we could just try in the series. What happens in here, you put in a -1, and then the negatives cancel, and the power doesn't care because it's just 1. So it's just 1 over n plus 1. So you're just getting the harmonic series. The harmonic series on this end. But what about on the other side? On the other side, you put in 1, and you're getting the alternating harmonic series. Okay? So, that one's going to converge. So we're going to put a convergence, we're going to put an equal sign here. So this should trigger you to ask a specific question. Like, whoa, hold on a second, what is happening over here? Could we just say that a second time? Yes, what we just said was, we said natural log of 1 plus x evaluated at x equals 1, which means, and after all, that's natural log of 2. We said that that is the following. Let's see what it looks like. X equals 1. I'm just putting in x equals 1. What is that? So you just pause that for a second, hold that thought. What is that? Does that look like something to you? It's the alternating harmonic series. So if n is 0, you get 1 minus 1 over 1. Okay, so I just found my mistake. Yes, I had to pause there to make sure. I'm going to continue and see if you can figure out what my mistake was, and then I'll go back and fix it. Okay, so when n is equal to 1, I'm going to get plus 1 over 2, and then this is going to continue like so. And this is the alternating harmonic series. But what's wrong? I should be starting with a plus 1, right? Otherwise, I'm going to be minus natural log of 2. That's no good. Okay, so I'll show you where the mistake is. Did you spot the mistake? When we took the integral, we forgot the extra minus sign because we forgot to divide by -1. So this negative is missing over here. Okay? And then actually everything else we said was fine. Okay, so there should be an extra negative there, and that's why we should have a negative there. So it's all good. Now it's all good. So you shouldn't believe everything you see on YouTube. You should think about what I'm saying. Okay, so there is another classic problem, which is arctan, and I'll let you mess with that yourself. But because it's based around the following fact, arctan of x. Okay, so you just continue this, and you should end up with just odd powers. That makes sense, right? If tangent is an odd function, then arctangent, in this case, because it goes through the origin, okay, it's going to be an odd function also. And it's going to inherit the radius of convergence. So, okay, you do it. And then, well, go on to the next video soon.